zoom in to help my older eyes, and we see we have sodium cyanide, and wherever we have sodium cyanide, I'm just going to make it easier on us and get rid of that sodium and apply our negative. Now, what do we know? Well, first of all, let's talk about what this functional group is right here. This functional group is known as an aldehyde. And what happens when we have a carbon that is double bonded to an oxygen? Well, we have a partially positive carbon right here and a partially negative up here, because the strongly electronegative oxygen is pulling some electron density away from that carbon. So because we have our positive right here, our nucleophilic cyanide is going to love to come over and attack right here. And because it attacks right here, let me go ahead and redraw it just because I'm running out of room here. I'm just going to draw our aldehyde portion because it's going to be very difficult to draw the whole molecule and still have room. All right, so our cyanide comes over, it attacks our partially positive carbon. That's going to kick this bond up here. That's going to result in an O minus up here. And our O minus is not very happy, so that is going to go ahead and attack our acid. So let me again move over. And that's going to create our alcohol group. And we already had our CN come and attack, so let me put that right there. And also right here. And what do we know about the CN bond? It is a triple bond with that end. So this is the product that we are looking for, or at least this end of the molecule. So we're going to have a product that actually looks like this. So this right here is our product we're looking for. This is just the right side of the product. All right. So if we look at option A, we do have the CN bond, which is great. However, we still have the double bonded oxygen, and that is not correct. So A is wrong. Let's go ahead and move down a little bit. B, we have a double bond with an NNH. That is wrong, but we do have the alcohol. C, we have the alcohol, and we have our C triple bonded N. So this is correct. This is the right answer. D, we inexplicably have a methyl down here too. So that's just silly. All right, so C is the right answer. Let's go ahead and make sure the system agrees with us. And it does. It does confirm that we did this properly, and this is the mechanism. All right, let me go ahead and clean all of this up, and then I'll be right back with you to begin the next problem. All right, we're all cleaned up, and we're on to problem 2. We're still in the aldehydes and ketones reaction section here. Let's go ahead and zoom in and see what we have. All right, so in this problem, we have a 5-membered ring. All 5 members are carbons surrounded by 2 hydrogens. We also have a carbonyl, or C double bonded to O. We have HCN, which we know will become CN minus, and we have H2 as well, which is interesting. So just like before, we're going to have a partial positive on our carbon, a partial negative on our oxygen, and that's going to leave an opportunity for our nucleophile to come over and attack our carbon, which is going to push our pi bond up onto our oxygen, making it O minus. So let's redraw this real quickly. Our oxygen is going to come over, it's going to attack this hydrogen, and that is going to create our OH up here. And then we also have our CN right here. Now, here is where it gets interesting to me, because without the H2, I believe we can make a case for this staying like this. However, all right, however, with the H2, if we were to give it a metal.
Future Ryan here. I noticed while editing the video that I said tin. Tin can reduce a atom as long as it has an acid with it. It is a reducing agent. However, what I had meant for the H2 to be coupled with as far as a metal was something like palladium. Palladium will take the H2 gas, it will split the hydrogen molecules, and then that will allow those hydrogens to reduce the molecule I'm talking about in the video. So I just want to come on here quick, make that correction. So anytime you hear me say tin in the next minute or so, I know that should be palladium, not tin.
Then what we can do, and similar to what Dr. Kerr went over in our last semester, is let's say we have a metal. In a simplified explanation, is it separates our hydrogens, making them both available. So our H2 becomes separated. Now, this is interesting because what can happen here is that it can reduce our carbon and it could also reduce our nitrogen. And what will end up happening is we get this molecule where we have a CH2 and an NH2 that is also attached to our carbon. And that gives carbon its 4 bonds, it gives nitrogen its 3, and then obviously it has its lone pair as well. So I just find that absolutely fascinating. Now, what's interesting to me is that the problem did not give us metal to make that happen. So I'm not 100% sure if Pearson Plus wanted us to assume that this would be reduced. But I wanted to show anyway what could happen if we have our metal here. But as far as what we are looking for in an answer, because it doesn't go into the bond detail, we're looking for something that looks like this, whether that is a single or triple. So this is our answer that we are looking for. So let's go ahead and zoom out and find where that is. All right, so A has the alcohol. That's half right. We're missing RCN, so that's definitely wrong. B also is half right. We have RCN. We don't have our alcohol. C, we just have an H2. That's I see what they're doing here. But this is wrong. And then D, we have our answer. You'll see that this matches with this right here, and they didn't specify whether there's the triple bond here or the single bond there. Maybe because they aren't showing any lone pairs. Maybe that is their way of saying that there should have been a metal there that would separate your two hydrogens on its plate, like we learned. This is almost the exact same drawing that Dr. Kerr did last semester. And what this does is it allows us to have these hydrogens separated that can then do our reductions. But either way, I'm very confident that D is our answer. Let's go ahead and check answer. And that does say correct answer. So that is great. We got the correct answer, and we'll move on to the next problem. Okay, another topic we went over is nucleophilic acyl substitution. And I did find some problems that have to do with that. So let's go ahead and tackle this one. And we see this is happening under acidic conditions. H2SO4 is a strong acid. All right. So we know it's going to easily donate protons. All right. So the first step is that this oxygen is going to come over and it's going to grab one of these protons. And that is going to create a positive on the oxygen here. And then we go over here and we notice that we have our alcohol. And this has a lone pair right here. And that is going to go ahead and attack the partially positive carbon right here. Now this bond coming over is going to push the pi bond up, getting rid of our positive. Okay, so let's redraw what we have at this moment. We have a CH3, CH2, another CH2, and then we have our oxygen here. That's bonded to our H. We have our OH right here. And then below, we have our O, CH3. Let's not forget this is a positive. I forgot to write that because it has the H over here. And then this oxygen has lone pairs. We'll just draw one. And what that's going to do is it's going to come around and it's going to grab that hydrogen. And what does that make? Well, that makes a leaving group known as, and you may have never heard this before, this is such a rare molecule, water. And water is a great leaving group. It goes, this is actually something that happens quite a bit in the MCAT. This is called a condensation reaction. All right, I'm running out of time, so we got to hurry up here. One of the electrons from here is going to come down here. It's going to create a double bond. This hydrogen is going to leave via H3O or other means, and we are going to end up with a structure that looks like this. And that is our ester. So this is what we're looking for in our answer. We want something that looks like this. So let's go ahead and take a look at what we have. Okay, so our first option has way too much going on. I can already tell that. Our second option, we have nope, this is wrong. This is the wrong place. Our third option, we have, nope, again, way too much going on. So it must be D just by process of elimination, but let's go ahead and see why. Let's see here. All right, so let's look at our structure right here. We have our CH3, yep, right there. Our CH2, yep, right there. CH2, yep, right there. C double bonded O, yep, have it right there. Then our O, CH3, have it right there. Yep, and the only thing they threw in two was our leaving group, the water, which we did over here. So this is the correct answer. D is the correct answer. Let's check. And that is correct. We did it properly. All right, that